Okay, so second part for today. Now, in this lecture, I would like to show you some examples of real-life problems where you could, or when someone have successfully used the manifold optimization procedures. So the first one is the three-dimensional reconstruction of a set of points from their projections. So what was the setting? There is a number of situations. For example, medical exams. I've seen a name in the list of participants, so I have to tell this. Medical exams, for example, you have tomography or X-rays or any other kind of medical exam like that, and you are projecting these rays from sources, and you have the result, which is a sort of projection, not always, but at least you have the projection. Or you could be taking pictures of an object from different angles, or stuff like that. So you have a set of points in R3, and you have projections of these points on planes. So for you have DJ1, DJN are the jth projection of P1, Pn. And you have a number of projections. Obviously, the less projections you have, the less likely is that you can reconstruct the whole set of points. So this is a shitty picture to show the idea. You have a real object. You have a real object here, and you project it from a point. This is the central projection, the usual, a fine projection. You project it on two different planes, and these are the data you have. The set of points on this plane and set of points on this plane, both written as points in R2, in two coordinates. In general, you have that the points are given by this function. So AJ is the projection function and is a matrix accounting for the internal parameters of the camera and taking the picture, so the focal distance and the skewness and stuff like that. RJ is a rotation, because the planes can be in different angles, and TJ are the translations which account for the center of the projection. So your problem is to find, given DJI, you want to find PJ, RJ, AJ, TJ. It's a lot of stuff. By the way, here I wrote down what a rotation means. So rotation means a 3x3 matrix such that the transpose is the inverse and the determinant is 1. Now, I don't want to go into the details of this kind of problem. And you can have different situations. For example, for a medical exam, in fact, most of the parameters are known. For a medical exam, you know everything. So, in principle, you should only invert the equation. The problem now is that the equation has what you could call gauge invariance. So, well, think about that. If you move everything, or if you rotate everything, the projections will be the same. If you rotate the points, the planes, and the centers, the projections will be the same. And there are other changes that you can do. Moreover, when you are taking the problem in the setting of diagnostic exam, X-rays or something, you have a limited number of sources. You cannot take the X-rays from 100 different angles or something like that. Whereas, for example, if you want to reconstruct an object from many pictures, you have like almost every possible angle you could imagine, usually, but you don't know many parameters, for example. You don't know the exact rotations of the planes. You don't know the distances. If you're lucky, you know the internal parameters of the cameras that took the pictures. Another kind of problem is what is called the cryo-EM, which is a technique to study proteins, so the structure of proteins. If you're lucky, proteins freeze up in more complex structures, like DNA or something like that, and they are constrained to take precise orientations and positions with respect to the other components of the structure. But if you are unlucky, and usually you are, proteins do whatever they want. So how can you study their structure? I mean, their 3D structure. Well, one idea is to freeze a thin layer of liquid containing the proteins. Yeah. And then, I mean, take an image via some sort of projection. I will write X-rays just to, I mean, so that we all understand, but no one will understand like that because they are not X-rays. They're something completely different. So it's called cryo-EM. Cryo is the freezing part. EM is the projecting procedure. But anyway, you project down this stuff and you get the two-dimensional projections of all the proteins, let's say. This is all the same protein, so it is the same three-dimensional structure projected down, but they are not constrained in any kind of grid or anything, so they can be rotated in many different ways. So you want to... Now, okay. We will keep this. So you want to get rid of rotations. So I mean, you froze all this thin layer of liquid with proteins inside, but each protein is rotated with respect to the other. So when you project it down, you get a lot of images which are to be matched one to the other, understanding that there is a rotation of R3 inside. Another situation where this can be, this kind of problem can be met is when you have a robotic device that doesn't have GPS, or I mean that doesn't need GPS, like a robotic arm or anything like that. I mean, a self-driving car without a GPS would be not exactly fun, but things that can move in the space and for which you cannot determine the exact position in the space. Also, things that you don't want only to account for the position in R3, but also the orientation. I mean, if you have a robotic arm or something like that, you want to know how it is rotating, which direction it is facing. Also for a car, you want to know which direction it is facing, not only the point where it is. So if you don't have a reference system from which to pick up these rotations, so particularly if you don't know the starting orientation of your device, you only have the relative rotations from one position to the other. So you're in a sort of situation like this one. It's not immediate that it's the same thing, but we will see it in a while, hopefully. So I will quickly go through the workflow for the 3D reconstruction from projections when you have many images. Like, for example, you go on Google Images and you download all the pictures of Rome and you want to reconstruct Rome. You want to reconstruct a 3D model of the city of Rome. Now, what you do? Okay, for every image, you extract relevant features. Now, if you are a pro in neural networks, you could extract semantic features, but usually you will just restrict yourself, also for time, to graphical features. Gradients, meaning not gradients in our sense, gradients of color, gradients of intensity, shapes, and stuff like that. For example, there is an algorithm called SIFT, S-I-F-T, which is a feature extraction algorithm. And for each image, you identify these features. Then you try and match features between different images. So you have two images of the same thing from different angles, but you can see they partially overlap. Okay? And you will say that two images overlap if you can match at least a minimal number of features. Then we determine what's called the fundamental matrix of every pair of overlapping matrices with random sample and consensus algorithm, RANSAC. I mean, if you want, you can. I mean, I'm giving you the names so that you can Google them. Okay, I lost the question. PJ, no. Yes, it's PI probably. Yes. Let's see. PI, yes. In the formula is PI. Yeah, no, but I don't care. I mean, no. Here there is an error in the formula. This is just PI. Because DGA is the jth projection of the first point. DJ1 is the jth projection of the first point. DJ are points in R2, DJI, and PI are points in R3. So yes, here should be PI. Thank you, Ruby. Okay. Now, for each pair of overlapping images, you find what's called fundamental matrix or essential matrix. There are two different things, but you can find either of them. And what do they do? Essentially, the essential matrix gives you a way to check correspondences. So it gives you a bilinear, a quadratic equation which has to be satisfied by the coordinates of point that corresponds to one to the other in different projections. So it's vague, but I don't want to go inside epipolar geometry and stuff like that. Third step, this is important when you have a lot of images. I mean a lot of images, like searching for Rome on Google Images, or if it were some years ago on Flickr. Okay, think about it. You search for Rome on Google Images. I bet you will find a lot of pictures of the Colosseum, from the Opio Hill, which is facing the Colosseum in the usual tourist side, and you will find less picture of the Colosseum from behind, whatever behind means, from Via San Gregorio, for example. And you will find even less pictures of a random house of a random guy in Rome. So, for the Colosseum, you have a lot of pictures, so you have a lot of data. You even have too many data. You can skim off a lot of pictures and still get all the essential informations. This is so you match all your pictures. You have a graph. You also have a dictionary from the features you extracted. You have a lot of information, of combinatorial information like that. You extract what's called the minimal set that gives you enough information to start with. And this is called skeletal set algorithm, usually. I don't know why it's not called minimal set algorithm, but whatever. Now what you do, you start from your minimal set, you travel your minimal set, you add more and more images to reconstruct your 2D points, and when you're done, you try and match all the other information if you need it. And this is the last step. So we solved the preceding problem. We want to find the PI, the RJ, the AJ, and the TJ. How? Well, we just try and minimize the function that given PJ, RJ, TJ, AJ, PI, RJ, AJ, TJ, and given DIJ, calculates the difference from the real, the data we have and the expected projection from our guess data. We try and minimize this function. Now, this is very complicated. There is a big part inside which is, I mean, we can get rid of the camera features. So the matrix AJ, you can more or less get rid of it. There are some procedures to get rid of the translation problem, so the TJ. The real problem is the matrix RJ. Now, you have the following. You have all your images, you know the camera parameters, you know the focal distance, the skewness, whatever, and you don't care about the translations. You can I mean, twist things so that you can ignore the translations. What you end up with is a lot of images taken around your object, and by having found an approximation of the essential metrics, you know more or less the rotation that brings you, the essential metrics is not exactly the rotation, but it's really, really close to the rotation that brings one image, one plane projection to the other. So you have two images, DJ and DK, and you have the rotation from DK to DJ, which is RJK. So it's a rotation matrix. So if you have n images, you have n times n minus 1 halves at most rotation matrices. Because for each pair of overlapping pictures, you have a rotation. Now, you would like to find absolute rotations. So you fix a coordinate system and you want to write all these projection planes like one rotation each from a given reference plane. So, given a collection of rotations, RJK, you want to find Rj such that Rjk is Rj times Rk minus 1. So if you want to go from the kth image to the jth image, you go from the kth image to the reference one, and then from the reference one to the jth image. So in this way, you're writing your n times n minus 1 halves relative rotations in terms of only n rotations. And this is more or less the fourth step of the algorithm, is the core of the fourth step. Now, this can be written in terms of minimizing this function. Given all the relative rotations, you want to minimize the function f of R1, Rn, sum over j and k of Rj minus Rjk compose Rk squared. this is a norm. I mean, you can take the Frobenius norm or the L2 norm on the matrices. I mean, more or less everything will do it. It will give you different cost functions, but the minimum will be the same. Now, this is a problem, an optimization problem on a manifold. With a small leap of faith, you can easily imagine that if you have two submanifolds of the Euclidean space, you can take the product of them. It will live in the product of the Euclidean spaces, and it will be again a manifold. So for example, if you have M inside Rm and you have N inside Rn, you can take the product. The product will live naturally inside Rm plus N, and this is again a manifold. How? Well, you can show it in many ways. For example, you just take the product of local parameterizations. So you parameterize M in the first M coordinates and N in the first N, and it gives you parameterization of the product. Or you can put together the defining function. Almost anything you do will work. No, okay, it's not deleting anymore. So SO3N, it just means the product of SO3 with itself N times. By the way, I don't know if I said that, but this is just the rotations of R3. Okay, so the matrices are the rotations of R3. Now, this is an optimization procedure. You can use what we explained before, not for what I'm showing you now. I mean, this is a result which was obtained in completely another way. It required a day of calculations on a multi-core system and whatever, but it's worth watching. I mean, this is the Colosseum reconstructed from pictures from the tourists on Flickr, I think, because it's not completely recent. The black dot you see are the camera positions. So you see every black dot is in fact a small tetrahedron, which a small pyramid, which gives you the camera from that point, with the focal distance, the skewness, the opening angle, or whatever. And this is a mesh reconstructed the Colosseum from just the picture of the tourists. Now, back to business, a special orthogonal group. So our SO3 is a three-dimensional submanifold of the 3x3 matrices, which is R9, given by this set of conditions. First thing first, for every couple of rotations, there is a diffeomorphism of SO3 that brings one to the other. This is quite easy to show. I mean, let's see how you could well, for example, if you take f of, well, I'm using too many times x. Okay, tilde. So this is just a linear function, because, I mean, okay, let's write it this way. F of r equals x prime x transpose r. So it takes every matrix and it multiplies it by a fixed matrix. This is linear on the whole set of 3 by 3 matrices. And if you restrict it to rotation matrices, it will give you again rotation matrices. And being linear, it's easy to verify whether it's a diffeomorphism or not. It just depends on the matrix here. Why is it important? It's sort of what happens on the sphere. If you consider the sphere, and you take 2 points, you actually have a rotation that brings 1 point to the other and fixes the sphere. So this is a map from the sphere to itself, which is a diffeomorphism, and brings 1 point to the other. So in some sense, everything that happens on a differential geometric viewpoint in 1 point, it happens also in the other point. So if you can calculate the tangent space at 1 point, you can bring it around on the whole manifold. So you have the description on the tangent space on the whole manifold. If you have a retraction that works in 1 point, it will work in every other point, etc., etc., etc. Secondly, the tangent space to the orthogonal, the special orthogonal group is this one. So the tangent space in X is the set of all matrices X times Y, where Y is antisymmetric. So is Y plus is skew symmetric, if you want. Y plus the transpose is equal to 0. So what's the idea here is that we take this function, which is a function from 3 by 3 matrices not really. Well, in principle, yes, but then GDX is symmetric, because, I mean, if you take the transpose of these matrix, you will end up with the same matrix. So you can actually write this from the 3 by 3 matrix to the symmetric 3 by 3 matrices. This is R9, this is R6. This is a linear space. Now, if we want to calculate the differential of G at X along a tangent vector Y, and the tangent vector in R9 is again, I mean, R9, so this tangent vector is a matrix, we have to calculate the limit for t going to 0 of this expression, well, minus I plus I minus the identity terms cancel out. And this gives you what? This gives you this. So you end up with this thing. Now, the tangent space, this is a defining function for our manifold, and so the tangent space is just the kernel. Now, what's the kernel? The kernel is a set of matrices Y such that, well, it's written in, let's write it like this. This is, well, it's okay like this. It's a set of matrices Y or Y transpose such that X Y transpose is antisymmetric. So you're just asking that X times Y transpose is antisymmetric, which means that multiplying by X transpose, Y transpose antisymmetric, that means that Y is antisymmetric. And so you have the condition I wrote you before. Now, you can also, using the first point we found, you can also just calculate this tangent space for X equal the identity, which is easier, I mean slightly, and then bring the tangent space around via this diffeomorphism, using the differential of this diffeomorphism, which is the multiplication by X. Now, less trivial fact, the projection on the tangent space of any matrix is this function here. So it's the antisymmetric part of X transpose U multiplied by X. Okay, this is the orthogonal projection. You can do the computations if you want. I will not. By the way, how do you write the scalar product here is the trace scalar product. So this is an orthogonal projection from the matrices 3 by 3 to the matrix 3 by 3. What is the scalar product? The scalar product between two matrices is the trace of AB transpose. With respect to this scalar product, this function is a projection. And you can easily see that the result lies in the space which we defined before. So this is an orthogonal projection with respect to this function. Okay. So orthogonal projection in the Euclidean space okay. Again, it is easily seen that the image is the tangent space we defined before because X times antisymmetric matrix. It's also easy to see that if you project the projection, you end up with the projector vector again, so it's idempotent. And if you take the what's left to Okay, you should verify that these holds. This is a computation, not really difficult. Hope I got it right. Now, the retraction. The last ingredient to work on the special orthogonal group, the retraction. This is a possible retraction, it's not the only retraction, but it's the easier to explain. So the retraction of, we write an element of the tangent space as x plus y. So the retraction of x times y at x is q, where qr is the composition, the composition of x plus xy. So you take a rotation matrix, you take a tangent vector, which is in the form xy, you sum them, so you obtain the applied vector, and it's a matrix. It's a 3 by 3 matrix. You take the QR, the composition of the matrix. I'm saying the QR, the composition, because I suppose that the diagonal elements of R are non-negative. And under this hypothesis, the decomposition is unique. So you have one orthogonal matrix Q and one upper triangular matrix R with non-negative diagonal entries such that this holds. Now, this is a retraction. Obviously, it takes values in the manifold. Obviously, if y is 0, it gives you back x. You only have to verify the differential hypothesis. The easiest way to do that is by calculating differential along curves inside the tangent space. I won't be doing that. There are other ways of, for example, the polar decomposition works or the Cayley transform works, but I don't want to enter in that. Now, with these ingredients, we can do optimization on the special orthogonal group. One thing you can do is what I showed you before, so the 3D reconstruction. Another task you can perform is a smoothing for video stabilization. So if you're taking a video with a cell phone or a tablet or something like that, sometimes the video jitters a bit, shakes a bit. This is usually due to small unwanted rotations. If your camera has, and almost every smartphone or tablet does, if your camera has a gyroscope, you can estimate the relative rotations between positions. So at every frame, you have a rotation from the preceding frame. A smoothing is a sequence of rotations that minimize this function. So what we are doing here, we are given the camera rotations, which happen, and want to find other rotations such that the distance from one rotation to the next one is controlled, but they also stay close to the original ones. So why? Because from one frame to the other, the camera could be rotating because you want to do a panoramic view, for example, or because you want to rotate. So you want to follow roughly the path given by these camera rotations, but you want to smooth it so that it doesn't shake. So you want to minimize the distance from one step to the next one. But if you only give this objective, then you will just stay still in one point on the special orthogonal group. You want to follow the path given by the actual rotation without shaking too much. Here there is a parameter, alpha, which depends on how much you want to smooth out with respect to how much you want to follow the original path. And D is a kind of distance on the spatial orthogonal group. You can take the norm of the difference. You can take the normal difference of the logarithm, the matrix logarithm. You can take a number of things. For example, if you know a bit, I mean, rotations can be parameterized with an axis and an angle, and so you could combine those to define a difference, which is called chordal difference, I think, chordal distance, I think. You can also write every rotation in terms of Euler angles and then take the difference. You get a lot of functionals. Now, which one to choose, it depends on, well, the aesthetic result in a way, but also on which is the easiest function for the optimization procedure. Because, I mean, the cost function dictates the success of your optimization procedure. So if you find something which is quadratic, convex, whatever, I mean, you have a number of what is this? Another problem where you can apply these techniques is the simultaneous localization and mapping. So you have a robotic device going around and it doesn't have a GPS. It as a gyroscope, you can determine the relative, the velocity and the relative rotations and stuff like that. So you can determine the relative positions, but you want to draw the global path of your small robot. Now, the rotation part is again solved with the optimization procedure we saw before. So we have relative rotations and we want to write them as composition of absolute rotations. So it's the exact same optimization that we met before for the 3D reconstruction problem. Also, if you think about it, as I was saying before, for a car, for example, your configuration space will be points on the plane, let's say, on the map, plus a two-dimensional rotation telling you where the car is headed. If you have some robotic device, more complicated, this will grow as configuration spaces. Maybe you have 2 degrees of rotational freedom and stuff like that. So you can you end up doing optimization on this kind of stuff. By the way, there is, I think, a paper, I think I've seen a paper at least, doing the stabilization video procedure exactly with the manifold optimization system and comparing it to the YouTube algorithm and other stuff. So if I find it again, I will put the reference in the material of the course. Now, an old classic. We take a symmetric matrix and we consider this problem, the minimum on the sphere of X transpose AX. The critical points of this functional are the unit eigenvectors of A, and the critical values are related to the eigenvalues exactly. Yes. Now, the unit sphere is the set of points which have norm 1. The Rayleigh quotient is, well, not exactly this function. The Rayleigh quotient is this function. That's why it's called quotient. X transpose AX over X transpose X. But obviously on the sphere, this is 1, so you end up with a quotient without the denominator. Now, the tangent space to the sphere, as I told you before, is just the orthogonal to the radius. The orthogonal projection is easy because you just project the vector on the radius and subtract that component. So identity minus the projection on the radius vector. and this is orthogonal projection on the tangent space. The gradient in all over n of our function is 2ax. So the gradient on the sphere, if you remember, is the projection of the gradient. So you have this formula. If you do the computations, you end up with 2ax minus r of x, x. And this is, and when this is 0, you get an eigenvector, obviously. A retraction is the one I wrote you before. And now you can write down an optimization algorithm to find eigenvectors and eigenvalues. And if you write it down, you will end up with the one which is given in almost all the textbooks of numerical analysis. And it's given there without thinking about manifolds and stuff like that. If you like, I mean, if you have fun coding and stuff like that, you can try to write this down, and you can try to write this down another one with this retraction. So let's see if I can. Okay. So xx times the cosine of the norm of v plus v over the norm of v times the sine of the norm of v. This is again a retraction. And this is the exponential map. But anyway, this is a retraction. So what happens when you change the retraction? The optimization algorithm, so the Riemannian gradient descent, with this retraction is surprisingly slightly faster. So you can compare, you can benchmark the algorithms, and this is slightly faster. By the way, if you okay, we haven't discussed a lot of stuff like what happens if you get a critical point which is not a minimum, so you can move again, blah, blah, blah. You could miss those points. And with the previous optimization procedure, you are only assured to find the minimum eigenvalue and the relative eigenvector. Now, you can do like in the proof of the spectral theorem, so you can restrict on the orthogonal complement every time, or you could do this kind of trick. You can define the function f tilde of x, which is the square norm of the gradient. Now, every critical point is a minimum for this function. So if you apply the optimization procedure to this function, you get an algorithm to, okay, let's say if you have a roughly approximated eigenvector, so you more or less know where the eigenvector is for some reason, then you can use the Riemannian gradient descent on this function to improve the approximation. You use that as a starting point and you improve the approximation. And you can do that with every eigenvalue, not only with the minimum eigenvalue, but every eigenvalue, because all of them are minima of this. All of the eigenvectors are minima of this function. Okay, and probably that's it. So, any questions? I'll stop the recording.